Hello, in this video I would like to introduce the notion of graphs. Actually, the theory of graphs is very interesting and very practical tool for mathematics. Before defining what a graph is, let us look at a small example. There are two islands, namely I1 and I2. This is a river. This is a bridge. So there are four bridges for I1 connecting this land 1, land 2. Also, one bridge to I2 and connecting I1 and I2. So there are 1, 2, 3, 4, 5, 6, 7 bridges. 7 bridges connecting land 1, land 2, island 1, island 2. Now, the question is, can we travel from this given any particular land to touching all the islands I1, I2, L2 and coming back to L1 without repeating the path on any bridge? We should not cross the bridge more than once. This is a problem which was posed in 1735 by a king in Prussia. A mathematician, famous mathematician, Euler, gave an answer for this, that it cannot be. A person cannot travel through all bridges starting from L1 to reach L1 only once. This is not possible. So, this is a small problem. There are many other problems of this kind, but before that, let me write down the definition of graph. A graph, I'm defining mathematically. A graph G is equal to V is an ordered pair of sets. It is an ordered pair of sets. 1. V is non-empty. It is a set, a non-empty set. The elements of V are called vertices or points or nodes. There are synonyms for this. The members of V are called vertices. V is non-empty. And E is a set containing two element sets such that A and B are belongs to V. Observe very carefully about E. I am writing a two element set which are members of E. Members of E are called edges. So, basically a graph is an ordered pair of sets where V is non-empty. Members of V are called vertices. E is all two element sets. Members of V are called edges. We denote the members of E by E1, E2 and so on. So the basic principle for this is E is an edge. E is set of edges. So I'll make a note. Two element sets, namely A comma B, is equal to E. So A and B are vertices. E is an edge. E is a line joining the vertex A and B. So we denote this by this way, AB. And this is E. I would like to see an example, a couple of examples on this. V is equal to ABC. I write E is equal to two elements at AB, AC. So I have two edges with three vertices. How do you depict this? Write down A, B and C. This is C, this is A, this is B. What is AB? It is a line joining A and B. What is the AC? It is a line joining A and C. So there are two edges. I can call this as E1, this as E2. So this is E1, E2. Observe that B and C has no edge. It was not connected by any line. Let us see. V is equal to A, B, C, and E is AB, BC. So again we can write down A, B and C. I'll write down A, B, C. Set AB is an edge. This two element set is an edge joining the vertices A and B. Similarly, BC. So you can observe that these two look alike. Suppose if I rotate this, this is A, this is B. I am writing this. C is here. So this is. The figures look alike, but they are not same because the sets are not same. AB, the set containing A and B, the set containing A and B are same, whereas the set AC and the set BC are not same. So what we can see is three element set with two edges. We have seen. Why can't we see a three element set with a three element edge? ABC, E is the set AB, BC, CA. So this is A, B, C, join AB, BC and CA. This is basically what a graph is. Now, before giving different types of graphs, let us look at one more example which will have a better insight. Look at this: A, B, C, D, if you look at this carefully, this graph, if I want to write down, now I will write down the sets. V equal to A, B, C, D, 4 element set. And I have to write E. What is E? E is set of edges. Set of edges means I have to write down in terms of 2 element sets. A, B, because there is a line between A and B. B, C, C, D, D, A, then A, C, B, D. As we all know, the set AB is same as BA. So you can see these two as endpoints. So another note is E is an edge with A and B as endpoints. That means if you see from this, A is an endpoint. If you see this, B is an endpoint. So E is an entity with AB as endpoints. Now, let us define two vertices in a graph G. Two vertices, namely U and V, belongs to V in G, in a graph G. Are adjacent if they are joined by a line, if they are joined by an edge or a line. Already these are all synonyms, edge, line. So here A and B are adjacent, B and C are adjacent, A and C are adjacent, C and D are adjacent. So in this example, in this C, D, in this, every pair are adjacent to each other. AB are adjacent, AC are adjacent, AD are adjacent. Similarly, DA is adjacent, DB is adjacent, DC is adjacent. So these are all adjacent pairs. An edge E belongs to E. Again, E is a 2-element set. An edge E belongs to E is called adjacent. Is called adjacent to another edge F in E. If an edge E is called adjacent to another edge E if there is a common vertex for both E and F. That is, look at this example. I'll write down only now A, B, C, D. This is E1, E2, E3, E4, E5. E1 and E2 are adjacent. Since B is a common vertex, Similarly, for A and C, D is another for A and C, D is a vertex which are common for E3 and E4. So E3 and E4 are adjacent. Similarly, E3 and E4 are adjacent. Now, can we find vertices without adjacency? Definitely. Look at this. Look at this example. This is V1, V2, V3, V4, V5, V6. E1, E2, E3, E4, E5, E6. The adjacent vertices are listed. E1 is not adjacent to E3. E1 is not adjacent to E3 because there is no common vertex for E1 and E3. There are two vertices in between, namely V2 and V3, but none of them is common to both E1 and E3. So there are examples which are not adjacent. These edges are adjacent. Now, let us begin with incidency. An edge E belongs to E. E is set of edges, E belongs to E, is incident to a vertex V in V if it joins V. If it joins, that's all. An edge E belongs to E is incident to a vertex V in V if it joins V. Let us see a small example of this. Two vertices A and B. This is E. So B is a vertex, E is incident with B and as well as A. So it is incident with both the vertices. That's why E can be counted twice. So degree of, before defining the degree of A, let me talk about this is what I'm going to define for a degree of a vertex. Let V belongs to V. The degree of a vertex V denoted by dV is defined as the number of edges incident to V. I have taken a vertex V, I am defining the degree of V. So degree of V is defined as the number of edges incident to V. Now look at this. What is the degree of A? There is only one edge which is incident to A. So degree of A is 1. Similarly, degree of B is 1. What you have to observe right now is E contributes for A and as well as B. Now a sequence of definitions. All definitions I am writing. A vertex V is said to be even by odd. I am writing two sentences at one stroke. A vertex V is said to be even if degree of V is even. A vertex V is said to be odd if the degree of V is odd. 1, 2, 3, definition for a vertex V is said to be a vertex V is said to be isolated if degree of V is 0. That's an isolated vertex. Definition 5, a vertex V is said to be pendant if degree of V is 1. Now we have all the possibilities. Pendant vertex, the degree of V is 1. Isolated vertex, the degree of V is 0. Even vertex, if the degree of V is even. Odd vertex, if the degree of V is odd. Let us see a couple of examples about this. Look at this. Example 1. U, V, W, X. Let us evaluate the degree of U, degree of V, degree of W, degree of X. I'm looking at the degree of U. It is the number of edges incident to U. How many edges are there incident to U? Degree of U is 2. How many edges are incident with V? 1, 2 and 3. So degree of V is 3. What about degree of W? It is 2. And degree of X is again 3. Let us observe one more thing. Let us see the sum. The sum is du plus dv plus dw plus dx. Let us see the degree. This is 3 plus 3, 6 plus 2, 8 plus 2, 10. So sum of the degrees of the vertices in a graph, in this particular graph, is 10. Observe number of edges. I can call this as E also, E or capital E. This is only for contextual meaning. Contextual writing. E, if I write capital E, number of edges. Small e, number of edges. Even single E is an edge. So number of edges E is 1, 2, 3, 4, 5. One more example. U, V, W. What is degree of U? There are two edges which are incident to U. Similarly, V is 2, W is 2. So if you take the sum, I'll write down sigma d u in V. Means du plus dv plus dw, which is 6, which is 2 times the number of edges. There are 3 edges. I have the same old example. V1, V2, V3, V4, V5, V6. And I have this. I'm just joining V2 and V5. Let us see degree of V1. There are 2. Degree of V2 is 3. And degree of V3, 2. Degree of V4 is again 2. What about degree of V5? 1, 2 and 3. There are 3. So what is V6? Now, what we can observe is the degree of V1 is 2, so V1 is an even degree, even vertex. V3 is an even vertex, V4 is an even vertex, V6 is an even vertex. What about V2 and V5? They are odd vertex, odd vertices. Again, what is the sum? Sigma dV, I'll write down. dV means this degree of V1 plus degree of V2 plus degree of V3 and so on. This is, look at this. This is 2, 2 plus 2 plus 2 plus 2. This is 8, 8 plus 6, 14. So, I can see this as 2 times. How many edges are there now? 1, 2, 3, 4, 5, 6 and 7. So 2 into 7. Again, V1, V3, V4, V6 are even vertices, V2, V5 are odd vertices. Let us see an example of, call this as U, V and W. What is degree of V? Degree of V means there is only one vertex, one edge which is incident to V. What about degree of U? 2. What about degree of W? 1. So if you look at this, V and W are pendant vertices because their degree is 1. So V and W are pendant. I will just 5 is simply write like this, U, V, W, X. U is even, degree of U is 2, degree of W is 2, degree of V is 2. So it is, all these are even vertices. X is, what is the edge, which edge is incident to X? There is no edge. So degree of X is 0, hence X is isolated. It's an isolated vertex. Now, an interesting theorem on this is, when you observe before writing this, look at all these things. What is, if in any graph G, if you calculate the sum of the degrees of the vertices, then it is twice the number of edges. That's what I want to see. I mean, this is just only an example, some of the examples we have calculated. I mean, we have seen. But now I want to see about a theorem which is called Handshakelemma. Now we have in any graph G, the sum of the degrees of the vertices is twice the number of edges. In any graph G, the sum of the degrees of the vertices is always twice the number of edges. Proof is very, very simple. The only thing is we have to make it in a formal way. Look at this. Observe this. This is not a proof actually, but the proof is different. What we have observed earlier is, if you take E, what is degree of A? Is 1. What is degree of B? It is 1. So degree of A plus degree of B is 2. How many edges are there? Only one edge. So this is 2 into 1. Suppose if you take 3, I mean different cases I am talking about. What is degree of A? Degree of A is 1, degree of C is 1, degree of B is 2. So degree of A plus degree of B plus degree of C is 2 plus 1 plus 1 is 4, which is 2 times how many edges are there? 2. This is not a proof, remember. This is just a model which we are seeing that given any graph, if you calculate the sum of the vertices, always it is twice the number of edges. How do you see this one? The proof is very, very simple. Now, the proof is, since each edge, now if you take this edge, this is contributing twice to its sum. Each edge is contributing twice, that means 2 times, twice to its edges. It's sum, means sum of the degrees. So if there are n vertices, it is hence sigma dvi I equal to 1 to n. Suppose if I have n vertices, each is contributing twice, so this is twice the E, where E is the number of edges. That's all. A very, very simple proof. What we have to observe is each edge contributes twice to its sum. That is called handshaking lemma. Let us see as a consequence of this. In any graph G, the number of odd vertices is even. What do you mean by odd number of vertices is even? That means you have even number of odd vertices in any graph G. That is, there are even number of odd vertices in a graph. Let us see the proof. I mean, let me make it in a, let V is equal to V1, V2, Vn. Let A is equal to V1, V2, Vt, the set of even number of vertices. Even number of vertices means each degree of each vertex is even. And BB, I am splitting it from Vt plus 1, Vt plus 2 and so on Vn. B, set of odd vertices. Set of even vertices, and this is set of even vertices, set of odd vertices. The claim is, what is the claim? There are even number of odd vertices. That means the cardinality of B, the number of elements in B should be even in number. That's what I have to prove. We know that V is equal to A union B. Now, I want to write down sigma dvi I equal to 1 to n. I have n number of vertices. Now I want to split this one. This is dv1 plus dv2 plus dvt plus dv of t plus 1, dv of t plus 2, so on, dv of vn. I'm just writing the sum. But by handshake lemma, we have twice the number of edges is equal to summation of dvi I equal to 1 to n. The total number dvi I equal to 1 to n is twice the number of edges. So this is even, is equal to dv1 is even number plus even number plus. I'm writing simply d of vt. I'll write down vj. J runs from t plus 1 to n. Now, this is a simple consequence now. dvi is dvj, j is equal to t plus 1 to n is equal to, this is even plus even number of even. So even minus even, which is even. So the sum is even means vj vt are even. That's the proof. Now, this is which I have about handshake lemma and the determining the number of odd vertices in a graph and the basic definitions of. Now, in the next lecture, I would like to write about the types of graphs and its properties.